Okay, so when I say the word physics, what pops into your head? Probably dusty chalkboards, right? Maybe some super complex equations? Well, what if I told you it's also the secret code behind pure, unfiltered adrenaline? Today, we're going to crack that code and look at the physics of one of the greatest inventions ever, the roller coaster. Seriously, have you ever been strapped into that seat, your heart just pounding, and thought, what is actually about to happen to me? What are these invisible forces that are going to throw me around every single twist and turn? Well, I promise you, it's not magic. It's just a couple of really simple, really powerful rules of the universe that make this whole thing work. So before we can even talk about the loops and the drops, we have to start at the very, very beginning. How does that coaster car even get going in the first place? And that brings us to our first big idea, the science of a simple push. Or, as physicists like to call it, work. Now, in our everyday lives, work is your job, it's doing chores. But in physics, it's way more specific. Work only happens when you apply a force, like a push or a pull, and that force actually makes something move. So if you push against a wall with all your might, but the wall doesn't budge, you've done zero work. No movement, no work. It's that simple. And the formula for it is super easy. It's just two ingredients. You take the force, that's how hard you're pushing, and you multiply it by the displacement, which is just a fancy word for the distance it moves. So how much work gets done all depends on how hard you push and how far the thing goes. Let's apply this to the coaster. You know that classic clack, clack, clack sound as you're going up the very first hill? That's a motor, and it's doing work. It's applying a force to pull the car up. And since the force and the motion are in the exact same direction, up that hill, we call that positive work. It's actively pumping energy into the system. But, there are always forces that are fighting back. Things like air resistance, the friction from the wheels and the track. They're also applying a force, but it's in the opposite direction of where the coaster wants to go. This is what we call negative work, because it's trying to steal energy away from the coaster. And then there's this weird one, zero work. Picture the coaster on a perfectly flat piece of track, just moving forward. Gravity is still pulling the car straight down, right? But the car is moving forward, not down. Since that downward pull of gravity isn't helping the forward motion at all, it's doing zero work. The force has to be in the direction of the movement for it to count. Okay, so all that positive work the motor did, chugging that car up the huge hill, it wasn't for nothing. Doing work is really just about transferring energy. By doing all that work, the motor gave the coaster a massive amount of energy, giving it the power to do something absolutely incredible. And this entire ride is basically a dance between two types of energy. On one side, you've got potential energy. Just think of this as stored up energy. It's the coaster car sitting at the very peak of the hill, just waiting. On the other side, you have kinetic energy. And that's the energy of motion. That's the coaster when it's absolutely flying down the track. Let's look a little closer at potential energy. The formula is mass times gravity times height. Now, the mass of the coaster and the force of gravity are pretty much staying the same, right? So the really important letter here is H for height. The higher that motor pulls the car, the more stored up potential energy it gets. That first hill is basically a giant energy bank. And then you get the payoff, kinetic energy. Now look at this formula. The key here is V for velocity or speed, but notice that it's squared. This is so important. It means if you double the coaster's speed, you actually get 4 times the kinetic energy. That little squared number is the physics behind that insane stomach-in-your-throat feeling of speed. So we've got these two kinds of energy, stored and moving, and they're constantly trading places all throughout the ride. But what's in charge of this trade? Well, it all comes down to one single, unbreakable, golden rule of the universe. And that is the law of conservation of energy. It's honestly one of the most important ideas in all of science. For our coaster, it means that the total amount of energy it has, that mix of potential and kinetic, it's locked in. It stays the same. You can't just make up new energy out of thin air, and you can't lose it. All you can do is change what form it's in. Let's see this in action. Here's the coaster, just for a split second at the very top of that first hill. It's barely moving, so its kinetic energy is basically zero. All that work the motor did has filled its tank completely with potential energy. It's maxed out, ready to go. And here we go. As the coaster starts to fall, gravity takes over. That potential energy is getting cashed in, and it's being converted directly into kinetic energy. Height is literally turning into speed. The coaster is going faster and faster, but if you look at the total amount of energy, It's exactly the same. And bam, at the very bottom of the hill, we're at our lowest point. Potential energy is now at 0. Every last drop of that stored energy has been transformed into maximum kinetic energy. This is that moment of pure speed, all thanks to that simple conversion. So we get it, right? Work builds energy, and energy transforms to create speed. But what makes the launch on one coaster feel so much more intense than another? Why does one lift hill feel super fast? That brings us to our last big idea, power. When it comes right down to it, power isn't about how much work you do, it's about how fast you do it. A more powerful engine doesn't necessarily lift the coaster any higher, it just gets it to the top in way less time. It's all about how fast you can convert that energy. The formula makes this crystal clear. Power is just the work done divided by the time it took. So if you want more power, you either do more work in the same amount of time, or you do the same amount of work in less time. And that's the secret to those modern launch coasters that just throw you back in your seat. They do a massive amount of work incredibly fast. It's actually really easy to mix up the units for power and energy. So watts and horsepower, they both measure power. That's the rate of energy use. Think a brighter light bulb or a stronger car engine. But the kilowatt hour that you see on your electricity bill, that's totally different. That's a measure of the total amount of energy you've used over time, not how fast you used it. And just to give you a little perspective, we still use the term horsepower all the time for big motors, like the ones on a roller coaster. And one single horsepower is the same as about 746 watts. So when you hear about an engine with hundreds of horsepower, you can just imagine the insane rate at which it's doing work. Which brings us to one last thought. We know the law of conservation says energy is never, ever destroyed. But every roller coaster ride comes to an end. It stops. So if that energy didn't disappear, where did it all go? Well, it was converted one last time. The brakes on the track did a ton of negative work, turning all that incredible energy of motion into other forms you can actually sense. The heat you can see shimmering off the brake pads, and that loud screeching sound you hear. The energy was never lost, it just changed its disguise.